All right, that's on that note, we can get started. So welcome back everyone to Compre 30. This is lecture 23, which is exciting because 23 is prime, and who doesn't like prime numbers? So before we get started, I'd like to give you today's Italian expression. Hello. But really, I've been told that I should have said Italian idiom all this time, but it's too late now. So today's Italian expression or idiom is the following. It's qualcosa bolle in pentola, which means something is boiling or brewing in the pot. But this is really meant to say something like a suspicious plan is underway or is brewing. Okay. And so what's an example of a sentence in which I use this expression and it's somewhat relevant to you? This is my sentence. I worked very hard to write it down. So whenever a student starts their question with, I know you're not supposed to check my answer, but Cesare knows that qualcosa bolle in pentola. So that's why I'm always very suspicious when a question starts in that manner. In terms of slightly more serious announcements, I have an announcement about Mercury, not the planet, but the course evaluations. So the Mercury course evaluations are out. And in case you've never filled out a Mercury course evaluation, it's an extremely long-winded form where there's like 50 questions that ask you about every single aspect about a course. And so despite how long it takes, I would really appreciate it if you could fill it out, because it would be really helpful for me to know what I should work on if I ever get asked to teach this again. Hopefully I do. For instance, there's been a lot of comments which have sort of come out through the midterm evaluation that I should work on my handwriting. I get that. Maybe I should take like calligraphy classes or something. Okay. Oh, and the other thing that I want to remind you is that assignment 6 is out. So it goes without saying that I really think you should start it early. I really think you should start this one in particular early because it's a bit longer. And I can't give you an extension past December 5th because we're just not allowed to give you extensions past the 5th. And also logistically, the final is the 12th. And so realistically, giving you a week to look at the solutions is probably the bare minimum, I would say. Okay, so that's in terms of serious announcements. Now, moving on to today's material. Today, we're going to be discussing Rice's theorem. So Rice's theorem, which was first discovered and proved by Henry Gordon Rice. In 1951. So he wrote out a proof in his doctoral dissertation, which is very impressive. But before we get to Rice's theorem, I'd like to refresh your memory and warm you up because it's cold outside with this warm-up exercise. So this warm-up exercise is a true or false. Hopefully it's straightforward. Suppose I have some decision problem A. So given some decision problem, let's call it A. I'm asked to determine whether the following statement is true or false, that A is C if and only if A complement is co-CE. Okay, so try to think about this for 15 seconds while I stare at you awkwardly and I count to 15 in my head. Okay, so what do we think? This was the reaction I was expecting. Yeah? Very good. So Louis says, yes, intuitively, because A means that you can verify yes instances, and a complement means you can verify no instances, but really it's the same verifier, right? And so that's perfectly right. So this is indeed true. This is indeed true. And I can quickly show you why, because for instance, if A complement is co-CE, then really by definition, so I get to write this if and only if, it means that its complement is CE, right? By definition. So for something to be co-CE, it means that its complement is CE. So that means that A complement is CE. But last time I checked, if you apply the complement twice, you just get back the initial thing you applied the complement to. And so in particular, you get A is C. And so this is definitely true. Okay. So this seems like a bit of a random warm-up exercise to start with, but it's really to get to allow me to talk about what we talked about towards the end of Thursday's class. So if you remember, towards the end of Thursday's class, we had started discussing this sort of undecidability hierarchy, right? So we said that there are problems which are undecidable, but they can either be CE or co-CE or neither, right? And so for instance, for example, the halting problem we saw is CE, right? We can verify, given a yes instance of the halting problem, that it is a yes instance. How do you do that? Just run the input string on M. No, I suppose it's the other way. Run M on the input string and just wait until it halts. Okay, but it is not co-CE. And this was actually due to a theorem by Emil Post. So this is really from Post's theorem, where in Post's theorem, we have that a language or a problem is decidable if and only if it's both CE and co-CE. But because we know the halting problem and its corresponding language are not decidable, right? Then if the halting problem is CE, it can't be co-CE because that would mean that it was actually decidable to begin with, which is not true. Okay. And so that was the halting problem. But we also discussed towards the end of class, and I didn't really talk about this explicitly, so that's why I'm talking about it explicitly here. We also talked about the not halting problem, right? So we talked about the not halting problem. And using this fact here, so using, whoops, no, I don't want to record myself. So using this fact here, since the halting problem is CE, it means that the not halting problem is co-CE. So it's co-CE. But the not halting problem is undecidable, which means that it can't be CE, right? So is not CE. Again, this is by Post's theorem. The other way you could see this, though, actually, the other way you could go to conclude that the not halting problem is not CE is you could just say, well, I'll just apply this fact on the fact that the halting problem is not co-CE. And so the negation applies in the if and only if here. So you could either show this via Post theorem or via the fact above. Okay. Okay, and so why is this useful? Why is this useful to know? Because we saw towards the end of class as well, towards the end of last class as well, that we can use mapping reductions not only to show undecidability, but to show that a problem or a language is not CE or not co-CE or neither, right? So recall that if we have a pair of decision problems A and B, and we have that A mapping reduces to B, if A is not CE, then this implies that B is not CE. Right? B is not CE. And similarly, if A is not co-CE, so if A is not co-CE, then this implies that B is not co-CE. And we used this fact, we used this theorem really to show that the fin problem was neither CE nor co-CE, right? So remember at the end of lecture 22, we showed that the halting problem mapping reduces to the fin problem with this extremely important technique known as bounded computation. And so by showing this, we showed that the fin problem is what? Not co-CE. And we didn't show this in class, but I posted the notes where we give a mapping reduction from the not halting problem to fin. And so since the not halting problem is not CE, then the fin problem is not CE. Okay, so that's what we did towards the end of last class. And so this actually allows me to refine this Venn diagram that I had presented towards the middle of lecture 22. And so I'm going to perform some magic. Oh, never mind. Damn, really? Oh, okay. I had copy pasted the, that's so lame. Okay, I have to redraw this. Okay, forget that I said I was going to perform magic. All right. Okay, so if you remember, we had this Venn diagram. Oh, that's so lame that it didn't work. Where the sort of whole collection of elements in this Venn diagram were languages, right? So this is really the universe here is all possible languages, right? And so for all possible languages, we have languages which are decidable. Oops. We have languages which are decidable, right? And so languages which are decidable, we showed through Post's theorem, are both CE and co-CE. And so we had shown last class that, for instance, the halting problem is CE, but undecidable. And so it's here. And so is the acceptance problem. And the emptiness problem is, in fact, co-CE, but undecidable. And remember, we had shown that through this technique known as dovetailing, right? So we showed this through dovetailing, another very important technique. Okay. And so now we can add further languages to this Venn diagram. So for instance, we showed that Finn is in fact here. And it can also be shown that a few of the other languages which we studied are also neither CE nor co-CE. We won't prove this formally in class because we won't have the time. But for instance, the EQ problem is neither CE nor co-CE. Neither is the all problem. Well, in other words, the all problem is neither CE nor co-CE. Similarly for the reg problem. And these two, the reductions are actually using the bounded computation idea. So that's why it's such an important technique, because it's used actually quite a bit in showing that problems are undecidable, and in particular are neither CE nor co-CE. And to add to this Venn diagram, we also have the complements of these decision problems. So I know that the halting problem is CE but undecidable. And so that means that the not halting problem is here, right? It's co-CE but undecidable. So the not halting problem is here. And so is the not acceptance problem, right? The not acceptance problem is co-CE but undecidable. And then similarly for the emptiness problem, because the emptiness problem is undecidable but co-CE, its complement is CE and undecidable. Okay, so this is a more complete Venn diagram. And so at this point, as is evidenced by this Venn diagram, we have studied many undecidable problems. So we've seen many undecidable problems. And most of these problems have something in common. And so this commonality is that the problem in question is about some property of the language accepted by some Turing machine, right? So we're not really asking a question about a Turing machine in particular. We're asking, given some Turing machine, what is some property of LM, of the language accepted by M, right? So this isn't really a question about the Turing machine in particular. It's a question about CE languages, right? Because CE languages are the languages accepted by Turing machines by definition or by theorem. Okay. And so, for example, in the all problem, right? In the all problem, remember, we were given some Turing machine M, but we were asking whether L of M was equal to sigma star, right? So we're asking a question about the language, right? So the question is about the language accepted by M. And not M itself, Okay. And similarly for the reg problem, right? So for the reg problem, we were asking, given some Turing machine M, is the language accepted by M regular? Right. And again, the same thing for the emptiness problem and for the fin problem, right? So in the emptiness problem, we were asking, well, is this language empty? And in the fin problem, we were asking, is this language finite? So what all of these decision problems have in common is that they're asking about some property, really, of the languages that are CE, of the languages accepted by Turing machines. So I'll get to you in a second. So now the natural question that arises, at least to me, is, are there any interesting, and so I'll tell you what I mean by interesting in a second, decision problems about properties of CE languages, so of languages accepted by Turing machines, which are decidable, right? Because so far, out of the 4 decision problems that we've seen, which ask about some property of the language accepted by M, they're all undecidable, right? So maybe there are some decision problems which are decidable, in which case that's pretty interesting. What are the decision procedures of those problems? Can we make some general claim about that? And on the other hand, if the answer to this question is no, every question you ask about the property of a C language is undecidable, well, that's also interesting. That's interesting because that means that you don't have to do a mapping reduction, which maybe is sad because I know how much you love mapping reductions. Okay. And so the answer is no. So the answer is no. In fact, when it comes to questions about properties of C languages, undecidability is the rule rather than the exception. So undecidability is the rule. And to that, I'd like to add this slightly more philosophical statement: impossibility is everywhere. Okay. And so if you'll indulge me in this brief philosophical aside, I think that this fact is pretty amazing. So, at face value, it doesn't seem all that interesting. Why is the fact that impossibility is everywhere amazing? Well, I think it's amazing because, we exist, right? So things are possible, right? This computer that's in front of me works. This projector off of which you're reading my amazing handwriting, it kind of works, right? And so despite the fact that impossibility is everywhere, through human ingenuity alone, right? Through human efforts alone, we're able to make the world work. And I think that's awesome, right? Okay. So a little brief philosophical aside. So for the remainder of most of this class, we're just going to try to make this statement here, this statement about any interesting decision problem of properties of C languages undecidable, much more formal. Okay. Yeah, I'll take the question, Nicholas. Yeah.
What is cannot? What is the right?
This thing? Oh, and not M itself. Yeah, that's right. So we're asking a question about the language accepted by M, not about, say, how many states does M have, right? That's not a very interesting question to begin with, right? And so maybe the one thing that I forgot to say is, what do I mean by interesting decision problems, right? Interesting questions. Well, that just means questions for which the answer isn't always yes or isn't always no, right? So for instance, asking something like L of M is a subset of sigma star, not very interesting, right? Because yes, that's always true. So, not this, not that. Okay, that's not interesting. Okay. Yeah. Yeah, well, it's a very high level statement. So we're going to make it more formal, but yes, go ahead. Impossibility is everywhere. Yes. Yes. Okay. Very good. Very good. Very good. Very good. Excellent. That's a beautiful question. So the question is, well, hang on a minute. hang on a minute. If we look at this undecidability hierarchy, within the CE languages, we have actually the subset of regular languages, right? And, I can make a DFA, right? I can make a DFA which accepts a language that's decidable, right? And so this is true, right? This is true, but it turns out when you formalize this notion of, say, creating a DFA that accepts a language, right? That's just some subset of, say, the acceptance problem, okay? So it's a subset of this decision problem of some property. So it's possible that you have a decision problem where for some subset of inputs, it's, decidable, right? You can do it. There's, heuristics. But we're saying in general, given an arbitrary instance, there's no decision procedure, right? So it's very possible that a subset of the inputs, there are heuristics that exist, but not for the entire set of inputs. Yeah, that's an excellent question. Yeah, very good. Yes?
Like anything about the concepts of non-continuity and non-language. Do we know about anything recording? Because we can, like, if we know it's supposed to be, we know it's confident.
Right.
But when you know it's not supposed to be, you can say about something.
So the question is, if, for instance, you know that a language is not code-y.
Does that make it complement like not?
Yes, it does. Yeah. Yeah. So yeah. So yeah. Yeah. Because of really this fact. Because of this fact here. Yeah. Very good question. Yeah. So the question, the answer to the question is yes. If, say, something is not co-CE, then its complement is also not CE. Yeah. Good. Very good. Okay. So let's make this claim or this statement about impossibility is everywhere, but that means that hope is everywhere at the same time, much more formal. Okay, so let's do that by first defining what a property of a CE language is. So let's be given some non-empty alphabet. Given that non-empty alphabet, we say that a property P of CE languages, let's call that L sub CE, defined over sigma star, is really just a function or a mapping, right? And this function or mapping looks like P, and it takes some input of type CE language. So to write this down, I'll just say any input to P is going to be some language. So it's going to belong to some set, but all the elements of this set are going to have some Turing machine which accepts it. Right? So there exists a Turing machine M that accepts the language. Right? And so this is the set of CE languages. Right. So the subtle point is that elements in this language aren't strings, they're languages. Right? So it's a family of languages. And so then the property is given some language, which is CE, and then returns either true or false to say, yes, this language satisfies this property, or no, it doesn't. And because we want to be fancy, we're going to use slightly different symbols for true or false. We're going to use the top symbol, which just really looks like true, and then the bottom operator for false, right? So this just means true, and this just means false. Okay, so these are the widely used symbols in logic for true and false. Okay. And so pictorially, if you want to represent this, suppose you have all of the possible languages defined over sigma star. So that's to the power set of sigma star, right? And so within the power set of sigma star, you have the family of CE languages. So L sub C. Okay. And so now if I fix some property P, so I fix some property P, then for instance, if I have some language here, L1, then P of L1, well, that might be true. Okay. L1 might satisfy that property. I might have some other language. P of L2, which might be false, right? In which case, L2 does not satisfy this property. And so the important point I want to make here is that I'm talking about languages here, is properties of languages, but there are, of course, Turing machines which accept these languages, right? So for instance, for L1, there is a collection of Turing machines, in fact, an infinite number of Turing machines. Well, yeah, an infinite number of Turing machines that accept L1, right? So for instance, you have M11, M12, M13, and so on. So all of these Turing machines accept L1. And the property of L1 is its value is true. Okay? So that's an important point to remember, is that we're talking about properties of languages accepted by Turing machines rather than the Turing machines themselves. Okay, and so at this point, you probably want an example. Okay, great. So let me give you one. So we can rewrite many of the decision problems we've seen. So in particular, all of the 4 ones I listed before, you could rewrite them in terms of a decision problem about a property. So these decision problems which we showed were undecidable can be sort of rewritten by designing a corresponding property of C languages. Property of CE languages. Okay, so from now on, that's really what the term I'm going to use. I'm going to use property of C languages to talk about these properties. Okay. So what's an example? An example of such a property is, well, the emptiness property. Okay. So in the emptiness property, you have some non-empty alphabet, you have some language, which is a subset of sigma star, and that language is CE. Right. And then the emptiness property, well, the emptiness property, very simply, it takes in L, and it says true if L is empty, and false if L is not empty. Very simple. So then we can actually rewrite, for instance, the emptiness problem using this property P sub empty. Okay, so how we do that? Well, if we write the emptiness problem using this emptiness property, let's just call that empty prime. And empty prime can say something like, given some Turing machine M, is P sub empty of M equal to true. There's a mistake here. Yeah. Excellent. Very good. So there's a mistake here. The mistake is that what I've written is P sub empty of M. That's incorrect. P sub empty doesn't take a Turing machine. It takes a language. And so instead, what I need to do is I need to write P sub empty L of M. Okay. Because it's a property of the language, right? Like I was just saying. And so then we can also write the language corresponding to the emptiness problem, L sub empty prime, as the collection of languages, which contain encodings, binary encodings, let's say, of Turing machines, where the property of the language accepted by M evaluates to true. Okay. So it's true that I'm dealing with a language, right? A language that contains encodings of Turing machines, but to filter out the Turing machines themselves, I'm checking whether the property of the language accepted by the Turing machine evaluates to true. So I'm really emphasizing this fact that it's about languages, and that's just because it's very easy to confuse these things. Okay. And so now one question that might arise is, well, this is the definition, but how do you check that some property is of C languages? Is that what you wanted to ask? Oh, okay. Oh, yes.
Well, we already been describing FP and the
Yeah.
Property of that, the property of all process, the regular, whatever.
Uh-huh.
Why are we now putting it in an equivalent?
Why are we doing this? Because there's a theorem that requires us to formalize this, and then the theorem allows us to really unequivocally say that this is true. This is mathematics. You do this. I don't know what to tell you, man. It's gonna be okay. It's gonna be fine. You'll see. It's amazing. The proof is really fun. Okay, do you believe me? Not yet. Okay. All right. So how do you check, right? How do you check? Because I'm just giving you the definition, but how do you really check if a property is a property of CE languages? Okay, how do you check this? Well, the intuition, right? The intuition is because it's a property of languages, of CE languages, it should be implementation independent, right? It should always evaluate to the same value, regardless of what Turing machine I'm giving. I'm giving it that accepts the same language, right? So it should be implementation independent. And for those of you in say more applied programs like in software engineering, this kind of makes sense if you think about something like a functional specification, right? So you want given some input for your program to do some output, right? You don't really care about the implementation. The functional specification is satisfied as long as given the input, it does indeed give you the correct output, right? So regardless of the programming language, right? Regardless if for some reason you wanted to code it in assembly. Okay. And so you want to code it in assembly?
No, I was wondering. Why are we asking for the how we use the problem involved in the like administrator?
Yeah, I'll get to it. So the question is, why do we need to do this? Of course, if it's a property that intakes a CE language, then it must be a property of CE languages. Well, it's a bit more subtle than that. You'll see. It's a bit more subtle. Okay. And so we do need, in fact, this theorem because it'll really help us out when we look at the more subtle cases of properties of languages, I'll just say. Okay. So in this theorem, we're going to sort of state how to actually verify. So if I have some non-empty alphabet and some language defined over that alphabet, and I just have some property P, okay. You could just say some property P of languages, just to make it a bit more specified. Okay. Then what this theorem says is that P is a property of CE languages, if and only if, for every pair of Turing machines which accept same language, the following statement holds. So P L of M is true if and only if P L of M2 is true. Okay. So one of the reasons why we have to talk about this is because sometimes what people do is they define properties of machines, right? So they define properties of machines and then they generalize that to properties of languages. And so the generalization to property of languages is really through this theorem. So this could also be a definition. Yeah. Mm-hmm. Right. See, right. Well, let's just get to the too skeptical. I know what I'm doing. Okay, we'll get to it. Don't you worry. All right. Okay, because yes, obviously this is true, right? Obviously this is true. The proof is going to be, well, you know, otherwise P wouldn't be well defined, right? Otherwise, this must be true because P would not be well defined. Meaning that you could give the same language to P, and then sometimes it would give you true, and other times it would give you false, right? So that's clearly not well defined. Okay, let me get to the examples. Let me get to the examples. Okay. Well defined, since it would return true or false, depending on the language. Well, let's just say LLM1 or LLM2. Okay. So that's not well defined because I'm giving you the same language, and sometimes it's giving me true, other times it's giving me false. It's clearly not a well-defined function. Okay. So now to get to some examples, because I realize that this might not be intuitive, will be in a second. So suppose I define the following property, right? So I define the following property, and I define it for a language accepted by a Turing machine, right? That's a C language, right? So I define the property P sub 330 for L of M, right? So I'm given some Turing machine M, and I define a property of C languages as P sub 330 of L of M, right? This is a C language, right? And so let's define it as saying, well, it's true if M accepts 0, 330, right? So the letter 0 330 times, and false otherwise. False otherwise. Well, in this case, of course, this is a property of C languages. Why is it, of course, a property of C languages? Because it is implementation independent. Okay. So if I have, say, two languages, M1 and M2, such that L of M1 is equal to L of M2, right? Then for it to be a property of C languages, then I should have that, so I want to show, I guess, I want to show that P of L of M1 is true if and only if P of L of M2 is true. Okay. Well, let's start with the if then. Really, this could be a bidirectional proof. So if P of L of M1 is true, well, that tells me what? That M1 accepts 0, 330, right? So it seems like I'm asking something about the Turing machine, right? Saying that M1 accepts 0, 330. But if M1 accepts 0, 330, by definition of L of M1, it means that 0, 330 is in L of M1. And because L of M1 and L of M2 are the same, it means that 0, 330 is in L of M2. Okay. And that means, again, my definition that M2 accepts 0, 330, which means that the property of L of M2 evaluates to true. And this is really bidirectional, right? You can make this claim from right to left as well. So this is really, these are really if and only ifs. Okay. And so yes, in this case, I do have a property of C languages, despite the fact that it kind of looked like it was asking about Turing machines, right? So it's asking about the Turing machines that accept the languages, right? So a property of C languages regardless. But it ends up being implementation independent. So now the natural question is, well, what's an example of a property that kind of looks like this, but isn't a property of C languages? So let me give you an example, which at first might surprise you. Let's see. So in this other example, consider this following property. So given a Turing machine M, we define the property P prime of 330 of L of M, right? So again, it's of C languages. And we say that it's true if M rejects 0, 3, 30, and it's false otherwise. Okay. So my claim is that this actually isn't a property of C languages. Does anyone see why? Yeah.
Well, it's a big difference.
Very good. Excellent. Very good. Thank you, Stefan. So the comment is, it doesn't make any difference to the language that's given to the property, whether it being the Turing machine loops on 0 through 30 or rejects. And so the languages could be the same, but the behavior in a Turing machine could be different. Yep. Right. And so then the property of L would either be true or false, depending on what implementation I gave. So to see this slightly more formally, so the claim here is that P prime of 330 is not a property of C languages. Right? And that's because I can create two Turing machines. Let me create these two Turing machines, which for M1 on input W, if W is equal to 0, 3, 30, it rejects. And otherwise, it accepts. So let's write, come on, it accepts. Whereas for M2, we'll say that on input W, if W is equal to 0, 3, 30, then you make M2 go into some useless infinite loop. And otherwise you accept. Okay. And so in both cases, L of M1 is equal to sigma star, whatever sigma star is, minus 0, 3, 30. Right, so this is the case for L of M1 and L of M2. But now the property of L of M1, well, that evaluates to true because on 0, 3, 30, M1 rejects. Right? Whereas the property of L of M2, evaluates to false because given 0, 3, 30, the machine M2 does not reject, it loops. Right? So this is false. And so even though we gave P the same language, right? L of M1 is equal to L of M2, the property of P is either true or false, right? Depending on the implementation. Okay. And so that doesn't make it a property of C languages because it isn't implementation independent. Jacob, yeah. So the question is, when it's not a property of C languages, is it due to this looping? It's a bit of a hard question to answer. I think in many cases it's due to looping, but I hesitate to say in all cases. I can't think of a particular example off the top of my head. I don't like to say that things are general rules, but I think looping has to do with many of the examples that you can see, which wouldn't be C languages. Yeah. So for instance, I'll give you this exercise, which in this case does have to do with looping. And so just as an exercise, this exercise asks you to determine whether the following is a property of C languages. So given a Turing machine M, is P a property of C languages? Where P of L of M is equal to true if M halts on every X or input string X, and false otherwise. Okay, so I'll leave that as an exercise. So in this case, it kind of has to do with looping. More or less. Okay. And so that's kind of what we mean by properties of C languages. It's this really important point that they're independent of the Turing machines that accept the languages. Louis is still confused about the notation.
Here, prime. They can input a language.
Yeah.
No
So,
Turing machine is going to attach to that language.
so you could rewrite. Okay. Yeah. Yeah. So you could rewrite the property as there exists a Turing machine M which accepts it and which accepts 0 to 30. Right. You could rewrite that in the definition of the property.
But then, at that point, it is
No.
because no matter what.
No, because if we said no, it's because if we say given some language L, right, and then we say in the body of the if, right, so if we say something like, you know, if here, let's see, if there exists a Turing machine M such that L of M is equal to L and M rejects 0 through 30, right? Then I'm being given some language, which in this case has to be CE, right? And then, but this is implementation dependent, right? Because
Give it L of M1 and L of M2 is the same input, so the output also can be the same functions.
no, but there could be two distinct Turing machines which accept the same language, right?
That's fine, but in each case, the exists clause will be true.
Right.
There exists a Turing machine.
But there's an and. That's okay. Let's take this offline. Okay. I disagree with you. Sorry. Okay. Okay. So this is properties of C languages. Now, the last thing I want to say is I want to sort of formally define this notion of interesting property. Okay. So before we said that interesting properties of C languages are undecidable. So really what we meant is non-trivial. Okay. So we said every interesting property of C languages was undecidable. And so what we really meant was we meant non-trivial properties. We meant non-trivial properties. Non-trivial properties of CE languages. Okay. And so, you know, well, what is a trivial property of C languages? Well, it's when the property always evaluates true or always evaluates to false, right? So given some non-empty alphabet, a property P of C languages is trivial if either for every language, which is a subset of sigma star, L is CE, implies that P of L evaluates to true, or for every language which is a subset of sigma star, L is CE, implies that P of L evaluates to false. Right, so this is the trivially true. This is the trivially true property of C languages, and this is the trivially false. Okay, and so for instance, one trivial property of C languages could be, you know, given a Turing machine, M is L of M CE, right? So we're asking, is the property of L of M when it evaluates true if L of M is CE, that's clearly a trivially true property of C languages, because for any language that you give it, that's accepted by a Turing machine, it's CE by definition. So this is trivially true. Because L of M is CE by definition. Okay, good. Any questions before we state the theorem? Okay, so now we're finally ready to state Rice's theorem, which really formalizes this notion of an interesting property of C languages. So we have the following theorem, which is known as Rice's theorem. And so it says, given some non-NP alphabet, every non-trivial property of C languages is undecidable. So this is how Dexter states it. I don't really agree with, well, this is one way of stating it, but it's a bit unclear what exactly is meant by a property being undecidable. So really what this is saying, what this theorem is saying, is that for every non-trivial property, of CE languages P, the following language is undecidable: L sub P, where L sub P contains all of the Turing machines, so all of the strings that are binary encoding the Turing machines, where the property of L of M evaluates to true. Right? So this, which is a subset of sigma star, and so it's a language, is undecidable. Right, so I find that this is a clearer formulation than just, the property is undecidable. Okay. So this is a theorem, so it requires a proof. And the proof is really not all that bad. It's only bad because I'm running 7 minutes behind. But I'll do it anyways, because it's fun. Okay. But before that, are there any questions about what the theorem is stating? Nope, doesn't look like it. All right. Okay, so let's prove this. And so the idea behind the proof is, well, I'm just going to take some arbitrary property of C languages P, and I'm going to then consider the language L sub P, and then do a mapping reduction. And the mapping reduction is going to be from the halting problem to L sub P. And if I have this mapping reduction, then because the halting problem is undecidable, then so is L sub P. And yeah, right. Okay. So the first part of this proof is just going to be the setup. So the setup is going to let P be some arbitrary non-trivial property of C languages. Now we're going to do something that seems very strange, is that we're going to assume something in particular about this arbitrary property of C languages, despite the fact that it's arbitrary. So the strange thing that we're going to do is we're going to assume that the property evaluated on the empty set returns false. And so this seems like it would cause your proof to lose generality, but you actually assume this without loss of generality. So you can do this without loss of generality, because if P of the empty set was true, then the following arguments would be symmetric. So it's not really obvious at the start of the proof that this is true because, what are the following arguments? But as an exercise, so I'll leave this as an exercise to check. If you say that the property of the empty set evaluates to true, right, then the rest of the arguments that will follow will just be swapping the true and the false. Okay? And so because the empty set is a C language, it has to evaluate to either true or false given that property. And so this is actually a safe assumption because of this statement here that the arguments are symmetric otherwise. Okay. So I have my P then, I have my somewhat arbitrary non-trivial property of C languages P. Now, since P is non-trivial, right? So it means that it's not trivially true and it's not trivially false. So it doesn't always evaluate to true and it doesn't always evaluate to false. Because here P of MT evaluates to false, I have to have some C language which evaluates to true. Right? Otherwise, it would be trivially false. Okay, so since P is non-trivial, there exists some language which is a subset of sigma star, such that L is CE, and the property of L evaluates to true. This must occur because otherwise it would mean that P was trivially false in this case. Okay, and so L is CE, right? If it's CE, that means that by theorem, there's a Turing machine, let's call it K, that accepts it. So since since L is CE, there exists a Turing machine K, which accepts L, i.e. L of K is equal to L. Right? Again, this is really just setup so far. So now what we need to do is we actually need to do a reduction. Right? So what we will do right now is we'll show that the halting problem, or the language corresponding to the halting problem, mapping reduces to the language corresponding to the property P, okay, L sub P. And so I'm going to rewrite L sub P to be the Turing machines that are encoded in binary, for which their property evaluates to true, for which the property of the language they accept evaluates to true. But I'm just going to use a slightly different symbol because the halting problem is also parameterized by an input Turing machine. So I'll use, let's say, N. So N is a Turing machine, and P of L of N is true. Okay, so I'm just using a different symbol because I'm going to use that the instance of HP is parameterized by MX. Okay, so now I need to do a mapping reduction, right? So remember the two steps to the mapping reduction is, well, the first thing is I need to convert some arbitrary instance of the halting problem, so MX, to some particular instance of the sort of L sub P problem, right? The property problem. To I sub LP, which is just some encoding of some Turing machine. And I have to do so, right? I have to do so keeping in mind that I need to show that M halts on X, if and only if the property of L of N evaluates to true. Okay. So I have to do the mapping reduction. And by do the mapping reduction, I really just mean I have to create the source code for N, given the source code of M and also the input string X, such that I'm able to prove 2. So this is what I need to do. This is a mapping reduction. So at this point, this is really hard because it's not like we're not dealing with a specific problem here anymore, right? We're just dealing with L sub P. And so that's much more abstract than what we're used to dealing with. But it's really not all that bad because the ideas would probably be the same in that, if M halts on X, then P of L of N should be true. Right? Well, the only thing I know is that L of K is equal to L, and P of L of K is equal to true, right? So what that tells me is that if M halts on X, then N should act exactly like K. Because if N acts exactly like K, then the languages they accept are the same, and then the properties evaluate to the same thing, in other words, true. So that's the hint for a yes instance to a yes instance. For a no instance to a no instance, if M does not halt on X, so it loops on X, then I know that the property of L of N should evaluate to false. Well, the only clue that I have for that is that P of the empty set is false. And so the clue is that, well, if M loops on X, then N should not accept anything. In which case I do have a yes to yes and a no to no correspondence. And so that's exactly what I'm going to do when I create the Turing machine N. Okay. So N is going to be some Turing machine, which I'm going to create based on MX and also K. So MX are inputs. And you can think of K as some kind of constant. Okay. So K is like a constant which is given. Okay. And so N is a Turing machine. And so on input W, okay, it's going to do the following, and it's going to do the following, assuming a slightly different thing than usual. We're going to assume, just for simplicity, that N has two tapes. Okay, so it's not a single tape, it's two infinitely long tapes. And that's just going to allow the construction to be much cleaner. So you're probably thinking, well, doesn't that seem unfair? Two tapes sounds like it's more powerful than one tape. But as Prakash was saying, a few weeks ago, whatever feature you add to a Turing machine, it stays in terms of computational power equivalent to a Turing machine that we saw sort of during lecture 18, so the vanilla Turing machine. And so the reason for that is because, you can encode, say, a 2D tape into a sort of letters that map back to those 2D tape letters. That didn't make a lot of sense. What I meant to say, okay, so what I meant to say is, if you have a 2D tape, okay, so you have a column of letters, then you can just map that to a single letter. Okay? And you can actually create that bijectively, so everything's okay. That's what I meant to say. Less confusing now. Okay. So that's the assumption, is that I have two tapes. And so what I'm going to do is I'm going to first save W to tape 1. And then I'm going to load X. I'm going to load X onto tape 2. Okay, so I'm using two tapes. So I have W on one tape, X on another. And I'm going to run M on X on tape 2. Right. So M runs on X, right? And I, of course, need this if M halts on X, right? So if M halts on X, right? Well, remember, if M halts on X, then N should act exactly like K. So for it to act exactly like K, then it should just run the string W with K. So then run K on W on tape 1. Okay. So if M halts on X, then I'm going to use the code of K to run W on. Okay. And so the last thing is that then if K accepts W, then the Turing machine N should also accept. Okay. So this is my construction of N. Now I'm claiming that this is correct. So let's actually check the yes to yes and the no to no answers. So if my answer to my halting problem instance was yes, then that means that M halts on X. M halts on X. So if M halts on X, that means that this if statement evaluates to true at some point, right? And so that means that regardless of the W, right? Regardless of the W, it will be run using K. Right? So then at some point, K is going to run on W, and then N and K are going to make the same decision on W, right? So K runs on every W, and K and N make the same decision on W, right? So meaning that K accepts W if and only if N accepts W. Well, that tells me that the language accepted by K is equal to the language accepted by N, right? But the language accepted by K was L, right? So this is then equal to L. And then the property of this arbitrary property that I had started with at the beginning, when it's given L, right? This L, which corresponds to the language accepted by K, it evaluates to true, right? So by assumption, P of L evaluates to true, but P of L is equal to P of L of N, right? So P of L of N also evaluates to true. And so this is my yes instance for the instance of the halting problem. And this is my yes instance for the L sub P problem. Okay. Okay. All right. So what about a no to no? So for a no to no, if I have that M loops on X, so if M loops on X, then if we go back to the Turing machine here, right? So M loops on X, and so N does its thing, it saves W to tape 1, it loads X, then it runs M. But now M loops on X, right? So this if statement never evaluates to true, and so N just hangs there, right? And so for whatever W I give N, it's never accepted. Meaning that L of N is equal to the empty set. So this really means that N loops on every W. So that means that L of N is equal to the empty set. But now if I evaluate the property on L of N, then this is the same as evaluating the property on the empty set. And note, I can do this equality, right? I can do this equality because it's a property of CE languages, right? So, this equality is well defined because this is a property of CE languages. Right? But by assumption, P of the empty set, well, that evaluates to false. Right? And so then I have my no instance, and I have my corresponding no instance. So this was for the halting problem, and this was for the L sub P problem. Yeah. Yeah.
If something, then
No. So the question is, very good question. So the question is, are you allowed to do something in a mapping reduction, which looks like if M loops? Oh, I see.
if W
Yeah, that you can do, yes. So, right, so the question was, can you make the Turing machine loop? Yeah, you can, right, yeah. You can just throw it into some pointless infinite loop, right? So it's the same thing as, writing some while true with an empty body in your code. Yeah. Okay, good. Everyone got very quiet because we did this proof and it got very abstract. But hopefully it was more or less clear. Yeah? Okay, good question. So, what happens if K does not accept W, right? Well, either it rejects W or it loops on W. But in either case, W is not in L of K. And so in either case, W is not in L of N. So that works out, right? Because for L of K to equal L of N, then for every string in L of K, it also has to be an L of N, and vice versa. And so this does that. Yeah. Yeah. Yeah.
General, like notation.
Uh-huh.
Whoever knows, right, like, oh, instance of the whole problem is yes or no.
The answer. I mean, the answer to the instance of the halting problem is yes or no.
So the answer to the instance of the whole problem is yes or no. You typically write just a Y or N.
Yeah.
But you use N fairly frequently to represent the other Turing machine you use. It's a little bit-
Oh, I see. So, no.
Well,
Oh, I see.
but
You're giving me this feedback now? After 3 lectures of reductions? So you write it in the Mercury course evaluation. Okay. Noted though, noted. Thanks for the comment. Okay. So with 10 minutes left, I would like to show you why you should care about the Rice's theorem. So maybe you didn't care all that much about the proof for the Rice's theorem, but you should care about the following thing because it allows you to show that something is undecidable without doing a mapping reduction, which is nice. So who cares? Well, we care because we can use Rice's theorem to show undecidability. Okay, so how can we do this? To do this, well, suppose we want to show that some decision problem A is undecidable. So we want to show that A is undecidable. And so then to use Rice's theorem, right? To use Rice's theorem, we'd like to essentially create some non-trivial property of C languages. Right, so we need to do 2 things, right? We need to create the property such that it's non-trivial and that it's a property of C languages such that L of A is equal to the collection of encodings of Turing machines where P of L of M is true, right? Because if we can do this, then really we have a property, a non-trivial property of C languages, and by Rice's theorem, we know that this should be undecidable. So for instance, if I want to show that the emptiness problem is undecidable using Rice's theorem, so show using Rice's theorem that the emptiness problem is undecidable. Well, we could create the emptiness property, right? So P sub empty, which takes L, let's say, given some Turing machine M. So I'm slightly changing the definition here, just to make it more obvious that, I have some Turing machine that accepts the language L. And so this property evaluates to true if L of M is empty and false otherwise. Right, so really this maps back almost exactly to how we initially stated the emptiness problem. And so then I have this property, right, the emptiness property, and to use Rice's theorem to show that the emptiness property is undecidable, well, I need to show that this is a non-trivial property of C languages, right? So I first have to show that it's non-trivial. So it's non-trivial because I do have 2 languages which evaluate to true and false, right? So for instance, if I have the Turing machine M1, which on input W just rejects, and I have the Turing machine M2, which on input W accepts, then L of M1, well, this is empty, whereas L of M2, that's sigma star, right? And so then if I evaluate P on L of M1, this will be true. And if I evaluate P on L of M2, this will be false, right? And so it's important to actually start with Turing machines and then to show what languages they accept, because that shows that those languages are C, right? So, you know, it's obvious for this case, but if it was something slightly more complicated, like in your assignment, then you kind of have to start with Turing machines. Okay. So I have that this property is non-trivial. Now I just have to show that it's a non-trivial property of C languages. So that it's a property of CE languages. Okay. Well, how do I do that? I have to show that it's implementation independent, right? So given a pair of arbitrary Turing machines that accept the same language, the property should evaluate to the same value. So, you know, given some arbitrary Turing machines, M1 and M2, and suppose that L of M1 is equal to L of M2, then I need to show that, so I want to show that P of L of M1 is true if and only if P of L of M2 is true. Okay. Well, in this case, this is pretty easy to argue, right? Because P of L of M1 being true, well, that implies that L of M1 is empty, but because L of M1 is equal to L of M2, then that means that L of M2 is empty. And so then P of L of M2 evaluates to true. And this is really a bidirectional proof. So you could argue the same thing from right to left. And so, yes, I do have a property of C languages, which is non-trivial, which defines the language corresponding to the emptiness problem. Okay, and so by Rice's theorem, the emptiness problem is undecidable. Okay. Okay. Let's see. 3 minutes to do 3 pages of notes. Doesn't seem possible. Any questions? Yeah?
Some were asked if I really like not valid property was the one. I think those are the supplements, but like you can come up with the number of states.
Oh, yes, very good. Yeah. Oh, yes, good, thank you. So there was an earlier question about how can you characterize properties of languages which are not CE? And so one easy one would be something like a dummy example where you say, you know, the property of L of M is true if M has more than 10 states, right? But then this is implementation dependent because you could create 2 Turing machines that accept exactly the same language, right? But one has 10 states and maybe one has 1 state, right? For instance, for sigma star, right? So yeah, that's a good point. Yeah, thanks. Any other questions? Okay, so I don't have time to do the 3 pages of notes. And so what I'm going to do is just tell you what we're going to do on Thursday. So on Thursday, we're going to show that some of the decision problems about context-free grammars, so decision problems about context-free grammars, for instance, checking that L of G is equal to sigma star is undecidable. So this requires us to talk about this language known as vowel comps. And next Tuesday, we will discuss the post-correspondence problem, and I will also reserve maybe like 10 minutes at the end to talk about the final exam. So I'll use the last 10 minutes to talk about the final. Okay, so I think for the first time in 23 lectures, I'm letting you leave early by a minute. So thanks very much. See you on Thursday.